idea how you
So how's your whole trip? Did you go to some nice restaurants?
No, we went to the same place as every day.
Where were you headed that day I saw you? That's so weird because I just got off the plane and I took the bus downtown and I got off. Yeah, I ran into you.
Hey, brother, how are you? Look, you're good, thank you.
Other user?
What?
It's like how you log into other users. Do you join the roster 3 with open entry?
No. I'm spoiled by outstanding support and system administration in South Dakota, and I do not see similar service here, so I'm still running jobs there.
Oh.
Why do you have a problem?
No, I don't have a problem. I kind of checked the system and I'm wondering if I'm going to get caught.
How do you treat the system?
You do open MP?
Open.
That's harmless. Huh?
Yeah, it's so I want each processor to execute a part of a matrix manipulation and write out the result in a separate file.
Yeah.
So what I do is I use this very elementary procedure.
Is there same software using cluster?
I mean, it's because of my open MP ignorance.
So how do I treat the system then?
Well, there's this open MP directive that's really simple. Go for the ONT section, and within this section environment, you just define which part of the matrix you want done, and you can within that section you gotta specify your output file and the part of the matrix. That's that part of the matrix and puts it out in that output file. The problem with that is if you want to do your whole matrix, you gotta rewrite your directive. Over any part of the matrix you have.
But that's against system rules.
No, it's not. It's technically open MP code. But
No, they won't let you. It's administrative.
what it does is it randomly takes the process from the processor's rest. It doesn't, you don't like, I don't know. That's
Is that chooser processor
I
from
don't
the
know.
same
I don't
node
know.
or different
Uh-huh.
node? Is that chooser processor from the same node or
So it's
random
like-
from any node?
I have an idea. It's not scientific. It is a career and administration. You are looking for a job upon graduation, and you do not want to leave Fargo.
I can make Fargo.
But you would prefer
There's a job I will do.
the cluster 3 Thunder
Yeah.
Success will need a director. You can probably apply. After getting the degree, it would be sufficient.
They probably have people with computer science degrees.
You tell, I know how to treat the system, and I will not allow anyone to do the same.
I guess
I
now
don't
they
know
do
if it's cheating.
That's fine.
now
That's
they
fine.
are using so you can do anything what you want.
Okay, so what are we going to do today? Why are we here? Any suggestions?
Density matrix
No, we are not ready for it yet, but good general direction. I have shared a little code which is improvement of what we, well, maybe downgrade of what we did have before. But let's just discuss briefly and then go to programming and generating some data. So, what did we do last time? I know that we spent about an hour of discussing and writing equations and then 5 minutes for coding. But what did we code?
Perturbation and the interaction picture.
Yes, and no perturbation. Interaction picture, and we went away from perturbation theory, just evolution. So we are looking onto strong interaction with field in the regime where it is far from perturbative, when it is not small, and when there are these Rabi flops, right? When the external harmonic perturbation changes state of system drastically. And this can be done in 3 ways: by evolution operator and wave function, by density matrix, and by Bloch equations. So we are going to go easy path today and use our previous experience to analyze the system. So no new tools, old tools, but new regime. So we are going to look onto two-level system under strong field. Maybe the field can be not continuous but pulsed. And then we need to compute observables and maybe visualize them. So who needs it? Brandon knows the answer.
Who needs this?
Yes.
NMR people.
Yes, good, correct. So if you do NMR people. So what do NMR people? Brennan?
What?
So what do NMR people need?
So they do timed pulses to change the difference, to change the population of the state actually,
Uh-huh.
to change the excited state, and then I guess I don't know if they use this, but
Good. Do you hear him? So pulses change the population. Do they care about magnetization of X and Y? Population is like Z projection.
right.
Do they care about X and Y projections?
Yes.
Correct. Why?
Well,
If you move your screen away, then you will be yes. It is not seen in this display, but it will be on recording.
so I don't remember all the details of it, but they can shoot different pulses from different angles at the sample to get different types of excitations for different types of data.
Okay. But so in NMR you do have static field in Z, and then you have the periodic field in X and Y. is there magnetization? Does the sample have magnetic dipole or magnetization projection in x and y direction?
Yeah, but I don't think they're measurable. Not really, no.
Will the sample respond to perpendicular field in x and y if it will have zero magnetic projection in x and y? So just in order to be able to interact with oscillating magnetic field, it needs to have non-zero projection of magnetic dipole in x and y. So not only the intrinsic property of the system, but present current orientation of this dipole in x and y direction describes ability of the system to respond to the perturbation. Right? So it is.
I thought it was all about relaxation. You flip and you see how it relaxes, and that is the signature of the molecule. That's because of the precession frequency. What's it called?
Not only. Not only.
You don't only look at after the pulse, the relaxation.
We will cover it too. But now, free induction decay. What you're talking about, we will cover it. It is in the plan. But now I'm just trying to provide arguments that we do care about projections in x and y of the magnetic dipole.
Well, that's why there's precession.
So population is insufficient. You need something else, and this something else is important in order to keep describing interaction with the field. Hi Levi, how are you?
Good, how are you?
Just excellent. Happy to see you.
I have a question.
Yes.
So, from what I remember, in doing NMR, very simple NMR like experiments in experimental physics class, they were so simple, they were just for educational purposes. We just apply a magnetic field, turn it off, don't care what happens during excitation, and we just look at the relaxation of the system. That's not what is done in real NMR for professional purposes. Excitation will also give you some information about the chemical signature.
What we are going to do right now is more complicated experiment, but more simple calculation. What you are mentioning, the relaxation is a challenge to describe. Right now, we neglect relaxation and we see just instant, continuous driving. This pulse or pulse, then nothing, then pulse again, and response of this magnetic dipole to this driving field.
Okay.
Relaxation later.
Okay. But as far as an experimentalist that uses one of the big NMR expensive machines in CNC or that's all they look at the relaxation. Do they,
not only.
Not only.
Not only. So, Brendan, can you summarize what we discussed? What was most impressive in the past 10 minutes for Levi?
Okay, so we learned that this is important for NMR chemists, and the NMR people, when they put the sample, they don't have this projection of the magnetic field. They opt just Z, but the X and Y are going to be 1. And
Yep.
So the X and Y are important.
Perfect. You know the game of the broken telephone?
oh, that was a broken telephone.
You should secretly tell this information only whispering to the ear and then letting this information circulate among everyone and then coming back to the front and declare what you got. So we can propagate wave function of two-level system forward in the future, right? Now, and we also can, at each instant of time, we can visualize the inversion, the occupation of level 1, level 2, and see how it changes with time, right? But we may want to enrich our arsenal by telling what our projections to x and y are doing. How do we do it? I know it is after we write it down and program it will be super easy, but there is the inertia of thinking, and I also try to postpone this instant of time. Any suggestions? Any help? So we do need vector of three projections. And we want to obtain these three things out of the C1, C2 wave function that we know, right? And I'll take the easier part. I'll write down for this one, which will be C2 star, C2, and C1 star, C1 divided by 2. So occupation of state of upper state minus occupation of lower state divided by 2. And if you want to really tell about angular momentum and magnetization, you may want to put H bar for dimensionality in front. But how do we get the x and y projections? Anything you recall? Anything? Sine and cosine if you already know the answer. If we, for example, if we have continuous irradiation of the system, then it will oscillate by sine and cosine. But what if it is a pulse of unknown shape? Huh? So we do have.
Bit from the momentum come as the X matrix.
Yes, yes. Can you try to record?
No, I don't know where we need
Me too. I am at the same page with you. But you can be most brave of all of us.
I guess I can remember.
Just try to verbalize what you are finding and on this.
From the angular momentum, right?
Mhm.
Yeah, we did. I just remember the SZ is a real number and SY is a imaginary part. Something like,
Try, keep doing.
I guess something like this.
Anything else?
Here, over here.
Okay. I think we have a. Thank you.
Thank you.
We are doing a good memory exercise. He will be very correct if we do S plus and S minus operators. You did mention this one.
I guess here.
You know what a poly-spin is?
Good, good. Do you want to? So this is from Jared.
You want me to just tell you it?
Next attempt is by Brenton.
Okay. I can use my cheat sheet, right?
You just spin up.
These aren't right?
No, you just spin off.
So this isn't right.
You try it.
This is, no.
No, we're trying to take the C1, C2.
Uh-huh.
Oh, maybe.
This is into the center of the symbol.
Zero.
Huh?
One?
Minus one. Last symbol is minus one.
Yep, you're right.
Many thanks. You saved all of us. So technically they are called Pauli matrices, but from now they will be Gifford matrices.
Differently.
Gifford matrices.
Oh, Gifford. Oh, even though I took a picture from Paul.
Okay. Gifford Pauli. So, do you have an idea what those matrices are? I just want not to block it. So the Y is next in the row.
Not next.
You don't. You are. You're just physically next. You don't need to come up. You can just tell what they are. What are their goal? What is the virtue? How they can help us. You can consult with.
What do they do then?
Well, the projections of spin states for those axes.
Mm-hmm.
Along the axis.
Okay. So we can correct something. So what Brendan wrote to us are just operators in matrix form, right? And we do need to find expectation values. So we need to find expectation values of these operators with these coefficients. Like if you do need S sub x expectation value, then we will do C1 star, C2 star. Here we write this vector, and some people skip H bar, especially in atomic units. Zero, 1, 1, 0. C1, C2. So it is a prescription how to convert expansion coefficients of wave function into observables. So those are directly related to magnetization of your sample. If you do this calculation, make summation over all individual spins in the sample, like average over ensemble, you will get macroscopic macroscopic magnetization of your sample. So this is an important observable, and we do want to compute it at each instant of time. So we need not only populations of levels, but we need also this projection. For Sx, for Sy, when you plug in this operator, and for S sub z. For S sub z, you see it will be same as here. So we are going to run the code, well, take the code and add calculation of these observables and just plot them. That's a summary. I even do not know if you need to discuss anything. Let's you ask, you tell if something looks strange and needs more discussion.
We're going to do that at each time step or at the initial time steps?
Each time step. Anything else what is unclear or sounds strange, or if you are not, if you disagree with motivation, like, is there a sufficient justification to do this exercise? Okay. So we can program each of three in MATLAB, and at the end of the loop over time, compute these projections and store them into like accumulation line. Same as we did all the time. Like we'll have variable for average Sx at given time, and then we can do average Sx is what it was before, and then current value. And then there will be three functions of time that we will want to draw at the same time and see how they relate to each other. Ah, here's the way how I could project it to the bigger screen. Are you starting from where we stopped last time, or from the little script that I sent today, like 5 minutes before?
Whatever you sent.
Yes, yes.
How do you do conjugation? Because for Z it has no, for Y it has I's.
You can either type conjug, C-O-N-J, or you can just put apostrophe. If it is a vector, it will be unitary, like transposing matrix and conjugating all elements. Were you able to get this drawing when you run the code? So, what does it mean?
As you hit your pump, and your laser it goes up and it stays and you hit it again and then inverse, hit it again, pump, and it goes up down.
Okay, so this red and blue are yes, a population of ground and excited, and what is yellow? Yeah, in laser, or if it is NMR, then it is magnetic field in transverse direction. So you see, the central frequency is the same, but envelope function, the amplitude raises and goes down. And from what we discussed in class, what will be the area of each individual pulse based on pulse area theorem?
Pi over 2 times the frequency.
You are factor 2 wrong,
Pi
or
over
you are
4.
factor 2 correct, huh?
Pi over 4 times.
In a different direction.
Pi times.
Just pi. So it is the pulse that flips population completely from ground to excited is a pi pulse, right? And what the main consequence of this pulse area theorem that I forgotten to declare in class, that the result of the quantum state when the pulse is over doesn't depend on shape of pulse. It can be rectangular or it can be Gaussian, as you see here. But the final outcome is the same. Okay, I'm done with comment, and now I'll just follow the same program of programming this expectation values. So the goal is to enrich this figure by 2 additional lines, one for s sub x and another f sub y as function of time.
No. When you do S, X, X, Y, X, Z, where are those? Can you plot that? Like a video camera. Like what do you do? You said to, so I define the operator, I define the empty index, and then at the end, and say x, 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 y, x, z is equal to times you can do that expectation value, and then I amended the
Yeah.
you're going to amend that as you go. So F is just some Gaussian that multiplies
Yes.
multiplies those relations
Mhm.
against it.
Mm-hmm.
Why is it two-dimensional?
Huh?
Why is FF a two-dimensional vector? It has FF and F inside. And F is the actual function.
What do you mean? FF? Is
FF equals bracket FF.
no, FF is one-dimensional array.
I'm looking at line 30 of the code.
Oh, I already corrupted something. What does it tell?
Huh?
I already edited,
That's why I said.
contributed more lines.
Oh, okay.
Um, I look on this line or something
Oh,
different.
the next one, so it'll be the 52 in your. But then I said the next.
Oh, okay. So it means contribute new element to the one-dimensional array FF and increase size of the array by 1. Right, like reallocate. Originally it is an array of length 0. After first cycle it is length 1. It just gets bigger, 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 bigger.
Is this what we're supposed to have? Because I don't. It's the bottom one.
Yes.
So it's supposed to look weird.
Mm-hmm.
Okay.
That's just multiplication. So if you roll that column back behind the main base, which is roll more. No, you need to have you need to do this here. So psi plus b times operator times psi. That's what we see under your name. We did sx equals 1. Oh, I didn't do the 1 half. No, star is just multiplication. Yeah, sorry. Target returns. T2 is already saved. T2. Time step, number of time steps is already saved. You multiply this by v. You will do 2 times v1. If u is bigger, now copy this to the problem. So your time is self-taught it. So if you go online, like 90, when you do your first product, it's 2p times v1. What is your v1? v1 where the top is 2.5. So when you plot yours, it plots it. There's not the same unit. And I asked him if that's right. One. All v1. Yeah, so that's the same like that. Because your the expectation value. So if your C1 is bigger than your C2, so if C2 is 0 and C1 is 1, right, then you get negative 1 over 2. So therefore, that would be down here. If C2 is 1 and C1 is 0, then that would be 1 over 2 is 1 now. Right? No, hold on, it's still on. Subplot. So you have to go before your first plot and add this line. So you can replace that. I added close all, so everything closes when I run this. All the figures close. Oh, yeah, no. No. Here. Subplot 1, 2, 1. So above that line. Above that line. Yes. So above the first plot, I can enter. Subplot 2, 1, 1. And then before the next one, so go to this line 98, go to end, and then do subplot 2, 1, 2. And now so I like sub. I have 2 separate paths. This is the one. So that's why I subplot. You like to do those.
Do you get a figure similar to this one?
I saw the last
Good as I do.
I forgot.
No, like when you, I hate when a bunch of graphs have a whole bunch of crap everywhere. That's why some posters and like all around I hate so much because there's like 15 lines and you can't see anything. So it's better to subplot. So
Why are they different?
why what different?
When you like start small, something is small.
Because they're
Maybe it's not an equal point pulse.
no, but you have the I instead of one on the diagram. So then, when you do the time to get, when you do C1, when you do the coefficients time to get times the operator times the coefficients, that will change it. Right?
I think this problem is iterative, but this is calculation.
But no, mine's longer time. So I did 10,000. So if you see the red ones start out big, and then it shrinks and it grows, where the blue ones start out small, grow, and then shrinks.
Which one is X and which one is Y?
Um,
Only we can make one of them
X-
dash because the colors are hard to identify. You get figures
Oh, that may not work. Or I think it don't work. Back to so this is your X, this is Y, go to the X. So right between the X.
the other.
Yeah. The problem with this is it's going to overwrite the every time. So you want to close this. And now, yeah, that's what it doesn't matter.
After we end the meeting, I'm going to share whatever I was programming, just that you compare. But please do not replace. Name your new code and old code as individual name, and try to send it to yourself if it is not your personal computer, so that you have your repository of little codes. Yes.
I thought that if you, so when you do like dash, you have to specify the color, or can you just do this?
You can do this with two dashes. Like dash dash. Two dashes.
thought it-
Yes.
Oh, okay.
Good.
Is there a way to make the dashes smaller? Or is it just
There is, but it is not as quick.
when you're going to label your axes? And then you want, I think you can put green up front. Yeah. No, it won't work. So just put it in within, so like G dash dash. And I think you can do like dash dash G. I don't think it's picking on where it is within it.
G dash dash E fold.
I don't, no, that line width. The line width is the width. thing, the expectation value is not whether would it just be expectation value on the y-axis for the x, xy, and xz, or what would be
Which units?
no label? So the top is population.
Uh-huh.
What is this?
3 projections of
So
spin.
spin
Spin projections, yes.
What are you doing with this?
I'll tell you in a second.
I need that. We're making it pretty. So like I subplotted it. No, I'm just making it pretty because I hate having everything on one graph.
What are you saying? Yes, you want to do?
F at 5
X, P, or this is what they call P1, P1, P, Y, P, X.
What is the P? Population?
Right, yeah. P1 population, P1, P population.
No, that's the top. That's top.
But on the bottom, you also get P. Or it goes to 0 and 0.5.
So that's the projection Z. That's
On the bottom,
yeah. So it's X, X, Y, X, Z.
well,
Yeah.
Okay,
It's easy.
and the code is called PC.
No, you told it that.
Okay, let me attract your attention for a second. So after you are done with plotting all these 3 projections as function of time, you realize that if it is a 3 vector, why don't we actually draw the vector? Or at least point in 3-dimensional space, because there are 3 coordinates, right? So look at the board. So if you do plot 3, and then 3 functions one after another, it will draw a 3-dimensional trajectory, which will be like end point of the vector that connects origin with the vector of angular momentum, vector of spin, right? It will be a point on a sphere, but since it is a trajectory, this point will be browsing around the sphere. So I did it, and it does something like this. But right now, we did several pulses. If you want to do it for educational purposes, we may want to do like half pi pulse or just very small pulse and see how the value of this point, how the trajectory changes depending on the properties of the pulse. Okay?
Why
So
did you times it by 2?
because I wanted to be from -1 to 1, to have sphere of radius 1. And I will disclose a secret. I do not know how to draw a sphere of radius 0.5 in MATLAB. But to draw a sphere of radius 1 is a simple command, just sphere.
Oh. Also, it doesn't draw the sphere for it. It just draws the orange line.
Yes, the command that I showed does the orange line, but before I type sphere.
You animate it so you can see it all the time.
Next time, yes, we should do it. Levi wanted a project.
No, I don't.
Animation of the point on a sphere could be a very short and simple project, something like this. I haven't decided, but if I will think, I will think in this direction.
I'll think that one.
Oh, see, everyone is happy.
Yeah, because it's like a 5-minute thing.
Oh, 5 minutes.
Yeah, it is. That would be a 10-day thing. I just don't do it. I already have one video. It's 48 kilos. So we calculated that at every turn step. Which was that what? What do you think? This. So the stuff that's highlighted. Where the operator within is either 0, 1, 1, 0. It was?
Well, in different codes we call it different way. Like you called it PX, PY, PZ. Some of us called it as expectation value of like A, SX, A. But what is the question?
The code that was in like 34 the last.
It didn't have these projections. It had only occupation of state 1 and state 2, but no projections.
I bought the XPYPC. No, it is on there. It's on there. I tried to calculate them, so I went back to the code and I saw that they were already calculated, so I just bought them. Because you set up a all-side variable within the code, and then the code I downloaded. Here it is. Which that's called factorization. I was trying to do that with a loop, but I couldn't remember how my that's factorization. I looked up and they were already yeah. So I was wondering what everyone was calculating.
Oh, okay. Same. Yes. Yes. No. Good.
Okay.
I call it fine.
No. Do you remember when Dirk was talking about factorization?
What?
Dirk?
Oh, yes.
That I believe that's what he's referring to.
Fine.
No, vectorization. It's when you have a vector and you instead of doing a loop, you just multiply by a vector and you get everything. Where ours we did loop. I thought when I Googled vectorization that's what it came up.
What? Well, it is for what you are telling. It's similar to parallelization, right? And was he telling in the same context or about?
He said that when he was doing his PhD, everyone was doing vectorization, where now everyone is doing parallelization.
Okay, yeah. I think you are interpreting it in the right way. So I did send you the code with well, you did it yourself, but just so you have two options.
Okay.
Okay.
I didn't do anything.
Lucky you. No, you did a lot. You did intellectual breakthrough. You followed what we are doing and intellectually comprehended what we did.
No, but this is where he got it. This is where he got it.
Oh, you wanted the uncommon stuff?
No, it's not common.
No, it's just that
Oh, it just wasn't plotted.
P1 and P2 were plotted, but the XPY were there.